Hello, everyone, and welcome to today's webinar Transformers for a New Age Forecasting. Today, I'll be taking you on a journey into the fascinating world of how transformers are reshaping the way we predict the future. I am Gaurav Mahakud, a product manager at Rakuten SixthSense cognitive AI engine, working on providing immunity to IT operations with auto ops, the evolution of AI ops. The transformer networks emerged in 2017 and utilized the self-attention mechanism at full efficiency. Currently, the entire digital and AI industry wants to utilize the transformer networks and replace the current algorithms in use. We all know about the disruption created by ChatGPT. GPT, or Generative Pretrained Transformers, is a generative AI which can create new content based on the knowledge it holds from its learning. These generated contents are very similar to what a human might produce. The strength of generative AI lies in the ability to capture complexities in datasets, and hence it can create contents which are indistinguishable from human thought process. Let's take a quick look into its pretty amazing implementation. Google introduced BERT, bidirectional encoder representations from transformers. And the most useful implementation of it is the new search engine of Google. BERT behind the Google search engine helps in understanding the complex queries by humans to provide us with better search results, and even aggregate the information from the internet to summarize those search results. OpenAI's ChatGPT is a chat-based platform where users can throw in any ethical question and get the answers available on the internet. The GPT-4 even allows document uploads, where the questions related to the document can also be asked. Imagine its usage in analyzing organizational specific legal documents and how faster it will be to check and verify legal clauses with specific questions. AlphaFold is an artificial intelligence program by Google DeepMind, a subsidiary of Alphabet. AlphaFold uses transformers for prediction of protein sequence. DeepMind won the CASP 13 and CASP 14. CASP is Critical Assessment of Structure Prediction and is a worldwide experiment on protein structure prediction. This is a very impressive technology that helped in identifying a bacterial protein structure in approximately 30 minutes that had proven hard to identify in 10 years. Cognitive AI engine by Rakuten SixthSense uses transformers for solving major problems in information technology. With a transformer-based anomaly detection, forecasting, sequence and categorization, cognitive AI will beat the traditional incident management methods to prevent issues and provide immunity to IT operations. So, prediction and forecasting is a very powerful tool integrated into various aspects of daily lives, playing a crucial role in planning, optimization, and revenue generation. So, it operates behind the scenes in familiar places like GPS navigation system on our phones. They help us to avoid traffic by predicting where the traffic can be higher, where the congestion can be, and we reach at our destinations faster. In the world of online shopping, it suggests products which are similar to what we have browsed before, making our shopping experience better and recommending things or products which might best suit our interests. Energy companies also use real time forecasting to predict electricity demand and supply, ensuring efficient distribution and cost savings. And also in healthcare, doctors help or doctors take the help of predictions for the patient outcome and making informed decisions about treatment. In a sense, Real time forecasting ensures that we make smarter, more timely choices, ultimately saving resources, time, and maximizing revenue in our fast paced, data driven world. So let's narrow down the scope of today's webinar and know about the future of forecasting. Will there be a new benchmark of efficient planning, and where and how to leverage transformers to forecast? Let's take an example of tourism. This example is not centered around tourism, but its effect on airlines and airport operations. When a lot of people choose a destination for a vacation, the destination needs to prepare for all kinds of demand to supply for. Prediction can be applied on various factors around this scenario to better plan on all those demands. If the marketing of tourism is done right, then it can be predicted that how many people are going to choose the destination for their next vacation. And relatively, it can also be predicted that how much is the average expenditure going to be, which will increase the income in the locale, ultimately contributing to the revenue. On the other hand, to increase revenue, airlines route more flights to meet the increasing demand of flying to the tourist destination. Not only the number of flights, but the price of tickets are made dynamic for maximized revenue. Finally, the ripples then reach mobility, where there is a rapid rise on cab demands, with the expectation that any tourist would want to cover all the tourist spots in minimum number of vacation days. The prediction on these factors is formed using statistical analysis. Historical data is important to analyze the seasonality over a long period of time, which can be in years. But forecasting is also needed at a much granular level where operational efficiency is required. Operational efficiency is a challenge in those domains where events are very dynamic in nature. Day-to-day operations in manufacturing industry, IT industry, airlines and entertainment industry deal with many known unknowns and unknown unknowns. Let's choose to go deeper into the use case around airport operations. With the aid of statistical analysis, airport authority can get an idea of the number of people that can fly to that destination. But given the number of flyers, major decisions are made by answering questions such as how will ground operations look like during the peak times? How will the flight schedule look like? What's the average flight delays at each arrival? Will the passenger information system be up and available all the time? These airport operations are so critical that if planned decisions aren't taken on them, there might be issues related to security, customer satisfaction, and revenue losses. Accurate real time forecasting can significantly enhance airport operations by providing valuable data and insights to optimize various aspects of the airport's functioning. And here is how. For flight scheduling, real time weather forecasting allows airports to anticipate adverse weather conditions, such as storms or heavy fog, and adjust flight schedules accordingly. This helps reduce delays and cancellations, improving overall operational efficiency. In resource allocation, predictive analytics can forecast passenger loads and aircraft arrivals, enabling airports to allocate resources like staff, gates, and baggage handling equipment more efficiently. This minimizes wait times and congestion. For security screening, real time forecasting can help predict passenger traffic patterns, allowing security personnel to adjust staffing levels and screening procedures accordingly. This ensures that security checks are both thorough and efficient. And finally, real time forecasting can predict when maintenance tasks are needed for airport infrastructures. It's fascinating how real time forecasting can solve operational challenges. But the common question asked by every decision maker is, where do we start with forecasting? Is there a model that fits all requirements? To begin that discussion, let's start with basics. The most common technique is related to the time series analysis. It's an analytical technique that identifies patterns in data collected with respect to time. We call them data points. Each data point represents an event that occurred at a specific time, and its recurrence can bring out a pattern that can be predicted in future. Causal forecasting is based on the idea that there is a cause and effect relationship between the predictor, independent variable, and the variable you want to predict, the dependent variable. Regression forecasting, on the other hand, is a statistical approach that aims to establish a mathematical relationship between predictor variables and the target variable. Causal forecasting models can be more complex because they attempt to capture the underlying mechanisms driving the relationships between variables, whereas regression forecasting involves finding the best fitting linear or non-linear equation to describe the data. Causal forecasting can be applied to predict flight delays caused by bad weather, and regression forecasting can be applied to predict the demand in cabs if number of tourists increases, which may or may not be correlated. Let's take a look at few popular algorithms that have been used to forecast time series data and rank them on a scale of highly traditional, moderately modern, and modern algorithms. Autoregressive integrated moving average, ARIMA for short. They capture different patterns in historical data and can provide short term predictions. They can be updated when new data comes in. This algorithm is highly traditional, is slower in performance, and less accurate for shorter horizon predictions. Exponential smoothing. They give more weight to recent observations. They are highly traditional again and are best for univariate forecasting with low accuracy on capturing seasonality. Recurrent neural networks, or RNNs, are sequence to sequence algorithms. They can capture complex temporal relationships in the data. They are a class of neural networks and are moderately modern algorithms for forecasting. Long short term memory networks, or LSTMs, are also sequence to sequence algorithm that is an enhancement to RNN to remember dependency for a longer duration. They are modern algorithms that can be suitable for univariate forecasting effectively. Moderately modern techniques like recurrent neural networks, or RNNs, have been in use for over a decade. It proved the evolution of forecasting as traditional techniques were not that accurate. A recurrent neural network is a type of artificial neural network designed for processing sequences of data. It's a computational model inspired by human brain's ability to process and remember information over time. At its core, an RNN consists of layers of interconnected nodes or neurons, much like neurons in our brains. However, what sets RNN apart is their ability to maintain a hidden state or memory of previous inputs. Taking an example of speech in any language is a sequence of words. When we read a sentence, we generate context out of it. This happens when we remember the context of the first word in the sentence and then aggregate the context of each word as we read. At the end of the sentence, we infer the meaning. When we learn to read more and train ourselves to understand the context of different sentences, we can even predict the next word. Similarly, RNNs are also designed to remember the context of previous words using its memory. This allows RNNs to work well with sequential data, where the order of information matters, such as time series data, natural language, and speech. RNNs have been used for voice assistance as it can process the command received as a sentence. They have also been used in language translation and text classification or sentiment analysis. Let's understand the basics of RNN to compare it with modern algorithms. RNNs are efficient on shorter input sequence. Imagine you have a line of hidden states. We will refer to them as blocks. They are processing a sequence of data, like words in a sentence or values in the time series. The first block in the line receives the first piece of data from the sequence and passes it to the next block. This passing of information is like RNN's memory. Each hidden state updates their own information based on what they received and what they knew before. The process continues down the line block by block as the sequence of data moves forward. Each block shares their knowledge and updates it based on the new input or a word in the sentence. Because each block passes on what they know before, the RNN can remember information from earlier in the sequence even as it processes new data. This memory of past information helps the RNN make sense of current data in its context. But there are major limitations with this approach. First, vanishing gradient. As the information passes down the line, it can get weaker and weaker. Think of it like whispering a message from person to person. After several people, the message might become too quiet to hear or might lose the context. This makes it challenging for RNNs to remember things for a long time in a sequence because of their limited memory. Sometimes RNNs struggle with understanding complex patterns also because they have long gaps between them. And finally, training time is higher because complex data requires more number of layers, a greater number of neurons and epochs where the input is given only in a sequence. Hence, RNNs are inefficient for longer input sequences and are only efficient for shorter input sequence. And hence, we enter LSTMs. LSTM network is an evolution of RNNs. LSTMs are designed to retain or forget certain memory, which makes it more efficient in remembering context. LSTMs also work in a similar manner of passing the information but through memory cells. These cells are made of gates. For example, a forget gate can discard the information that is not required from the previous memory cell, and the output gate can decide what should be passed on to the next memory cell. This fixes the problem of vanishing gradient by selectively remembering or discarding the information to retain longer contexts. Apart from that, LSTMs take care of complex temporal patterns as they excel at recognizing patterns in data that has long gaps between them. Their gating mechanisms help in preventing and using relevant information, making them more effective for tasks involving irregular pattern recognition. It is highly important to understand how have the algorithms evolved. Why is the current AI more intelligent than ever? These are the few requirements that drive the evolution of AI algorithms. First, data complexity. Modern businesses and organizations deal with increasingly complex and diverse data. Traditional forecasting methods were designed for simpler, univariate time series data. New algorithms are needed to handle multivariate data, high dimensional data, and data with irregular patterns. Computational power. Advances in computing technology, including the availability of GPUs, graphics processing unit, and cloud computing, have empowered the development of more complex and computationally intensive algorithms, such as deep learning models. Third, real-time forecasting. With a growing demand of real-time decision-making, forecasting algorithms had to evolve to provide timely predictions that can adapt to changing conditions. Online learning and streaming data processing techniques have been essential in this context. The recent evolution has resulted in the creation of transformers. We will know what transformers are very shortly, but here is a comparison of performance. Performance can be evaluated based on these benchmarks related to the lifetime of models as compared to the usefulness of the model, the speed of inference, and the ease of training. Due to the drawbacks of LSTM in many use cases, like faster and accurate natural language processing, transformer networks were designed which has already generalized many NLP tasks in its foundation models, which is trained on billions of parameters. In the paper, Attention is All You Need by Ashish Vaswani et al. Describes transformers as a sequence to sequence architecture. It takes a sequence and produces another sequence. The transformers follow an encoder-decoder structure but does not rely on recurrence and convolutions. The techno world talks about encoder and decoders to be imagined as human translators, and each of them can speak only two languages. The first language is their mother tongue, which differs between both. Example Japanese and English, and the second language is an imaginary one they have in common. To translate Japanese into English, the encoder converts the Japanese sentence into other language it knows, namely the imaginary language. Since the decoder can also read that imaginary language, it can now translate from that language into English. Together, the model consisting encoder and decoder can translate Japanese into English. Generative pre-trained transformers are foundation models that are trained on a lot of data from the internet. They are specifically for NLP tasks. They themselves are so strong in generating new content because they are already trained on contexts related to everything that is present on the internet until 2021. The content generated by GPT is very much like that of humans because they do it autoregressively, meaning it predicts the next word in the sentence or a sequence based on its own generated words, hence maintaining the coherence in the sentence or the content generated. Let's take a quick look at how GPT processes the input and generates a content. Given a prompt to GPT, write a short essay on sustainability, GPT is going to accept the sequence of words in parallel. And here's the first advantage. Transformers can take the entire sequence altogether onto multiple layers, unlike RNNs, which accepts it one by one. The sequence is then converted to its understandable format called numerical embeddings. Positional encoders calculates the position of each embeddings. This helps it to understand the context and the order of sequence. Now that it knows the context of the embeddings, the attention layer with self-attention calculates the relationship between each word. This is the second advantage, where it decides which word to focus more on. In this example, it would be the word sustainability. It scores each word and creates the attention vector. The decoder takes the attention vectors from the encoder and maps it to the relevant vectors for which similar context already exists. And here decoders autoregressively predicts the next word with higher probability in the sequence. The sequence of words which are highly relevant to the input prompt are then presented as results. Since GPT is the foundation model for NLP, it is not viable for time series prediction. For time series prediction, another transformer-based algorithm called TFT is used. Even though the task is the same, predicting the next part in the sequence, the change in the type of data provided makes a difference. Hence, the transformer is now designed to capture variations in time series data. In the NLP use case, the GPT can predict the next words in the sequence, where the TFT can predict the next data points in the time series data. We use some of the algorithms to predict the sequence in the time series data and compared its results with the TFT models. The algorithms in comparison were Bayesian structural time series model named Prophet, autoregressive model named ARIMA, and transformer-based TFT models. The dataset we chose for this comparison is a throughput dataset containing the number of requests made to a particular API. We divided the dataset into two parts, train and test, and trained all the three models, and here are the results. Clearly, ARIMA failed to capture the variations and just plotted the moving average. Prophet was able to capture the seasonality, as it is good at capturing the cyclic patterns, whereas TFT models capture complexities in the data to show a much accurate prediction. Transformers can not only capture even the minor variations, but it also learns seasonality very well. And above all, the most appreciated feature of TFT is to take the static information that do not change over time to make its prediction accurate. This ability is called incorporating both temporal information, the time series data itself, and static information, features that do not change over time. This capability allows them to adapt to changes in the time series while considering additional context from static features. Here's how TFTs typically work with static information. Imagine you want to predict the future prices of different stocks in the stock market. You have historical price for each stock, including daily opening prices, closing prices, trading volumes, and other market-related data. Additionally, you have static information about each company, such as its industry, market capitalization, and financial health indicators. Now, given a scenario, if there is a sudden change in the government regulations affecting a specific industry, traditional time series models might struggle to immediately incorporate this information into their forecasts because they primarily rely on historical data. However, TFTs can use their understanding of this static feature, example the industry, to quickly recognize that the new regulations might impact certain stocks of that industry and adjust their predictions accordingly. As we are solving the challenges associated with IT operations with greater efficiency, transformer models play a crucial role at the core of cognitive AI ops. With all the advantages of transformers that we have discussed in this webinar, cognitive AI ops makes IT organizations immune from the issues that have occurred in the past and predicts similar issues in the future. With this, we conclude our webinar on transformers for the new age forecasting. Thank you all for attending the webinar.